Hi, welcome to another 4AC video. In this video, we continue with lecture topic 4. We look at, in the previous lecture, we actually look at AC power for a purely resistive circuit, a purely inductive circuit, and a purely capacitive circuit. And only a purely resistive circuit will have effective power being transferred. In other words, we can use the power. Whereas in a purely inductive or purely capacitive circuit, the power is basically just stored and transferred back to the circuit or to the system and back again. In other words, there is no effective power transfer. So if we were to look at a combination, a circuit with a combination of a resistor, an inductor, and a capacitor, then what happens? So we can apply the earlier theory that we have examined. Let's look at the total impedance of this circuit, right, where a resistor, inductor, and a capacitor are connected in series. So from here we can deduce the total impedance of this circuit, and we can get the polar version. That means we can get a magnitude as well as an angle. And if we were to take the source voltage, Vs, as the reference, we have an angle, then my current can be calculated, or the current to this circuit can be calculated using Ohm's law as Vs divided by the total impedance. So from here, I can then deduce that the current flowing into the circuit has a phase angle that is given by the initial angle of the voltage supply and the angle of the impedance that we calculated from the total impedance. Now, if the so-called the inductive reactance magnitude is greater than the capacitive reactance, then we have the angle from the total impedance will be greater than 0. Then the current, the angle, phase angle of the current will be less than the phase angle of the voltage. We say that the current is lagging the voltage, as in the inductive circuit. However, if the other way around, the capacitive reactance is greater than the inductive reactance, the reverse is true, and we say that the current is leading the voltage. Now, the average power of such a circuit can be computed from the similar formula that we have used earlier, where the effective power is just the RMS value of the supply voltage and the RMS value of the incoming current times the cosine of the voltage initial angle and the current initial angle. In other words, we can then say is the phase angle difference between the voltage and the current supply. So expanding that further and substituting using Ohm's law, we can get that P is equals to I square R or V square over R. Similarly, the apparent power of the circuit is just S is equals to Vs times Is. In other words, the maximum amount of power that is available for us to use. But the reactive power of the circuit is then computed as Q equals to the current square, magnitude of current square in RMS value, multiplied by the effective reactance. And the effective reactance is just the difference between XL minus XC. In other words, it's either IS square times XL minus IS square times XC, which is also just the reactive power in L, the inductance, minus the reactive power in C, the capacitance. So equation 27 gives us a very clear idea that reactive power for pure inductance is positive and for pure capacitance is negative. And equation 27 can also be written as Q equals to VL squared over XL minus VC squared over XC equals to VSIS sine the angle theta. In this case, the power factor is the cos theta, the phase angle difference between the voltage and the current. And we can also calculate it based on P divided by Vs times Is equals to Is squared R over Is squared Zt, or the ratio between the resistor and the total impedance. So it's a very useful way for us to determine this. And if XL is greater than XC, we say the power factor is lagging. If XC is greater than XL, we say the power factor is leading, right? Similar to our lab experiment. At this juncture, we have a example 4.1, which I will urge you to watch another video which is specially dedicated to explaining example 4.1. Bye now for this video. Thanks for watching. Look out for the subsequent video for lecture topic 4, AC power. Bye bye.